Hello everyone. Today I would like to talk about the power factor correction improvement in electrical circuit. This assignment is done by two of us, which is me, Norming Yao, and also Teng Bao Yu. First, to the introduction, what is meant by power factor? Power factor is an expression of energy efficiency. It is usually expressed as a percentage, and the lower the percentage, the less efficient power usage is. Why is it important? From efficiency, a low power factor indicates inefficient utilization of electrical power. It means more current is required to deliver the same amount of real power. The second one is to reduce the energy loss. Improvement in the power factor cuts down the energy losses in an electrical system. The next is the lower electricity cost. Several utility firms charge penalty for low power factors since this increase demand on their structures. And the last one is capacity optimization. Higher power factor allows more equipment to be connected to the same electrical supply. Next, the causes of low power factor might be caused by the presence of inductive loads like motor, transformer, and fluorescent lightning, which are commonplace in industrial and commercial systems. Draw reactive power and thus reduce the overall power factor. The non-linear loads such as electronic devices and variable frequency drivers can also lower the power factor. There are several methods of power factor correction. The first one is capacitor bank. Capacitor draw apparently capacitive reactive power which offset the inductive reactive power developed by inductive loads. The advantage is simple and cost-effective, reduce reactive power demands from the alternative. The second one is synchronous condenser. A synchronous motor runs overexcited to provide reactive power to the system. This balances the inductive load and improves the power factor. Its advantage is it is adjustable reactive power output and it can improve system stability, but the disadvantage is high initial cost. The third one is static VAR compensator, which is SVCS. SVCS are the electrical device which dynamic adjustment of rated power in the system maintain high power factor. Its advantage is real-time compensation and effective for fluctuating loads. The next one is harmonic filter. Harmonic filter can clean up harmonic distortion and raise the power factor when non-linear loads like variable frequency drivers and electronic equipment generate harmonics. Its advantage is to improve power quality and reduce loss caused by harmonics. The next one is balancing load. The load of a three-phase system can be distributed among the phases in such a way as to improve the power factor by reducing neutral currents and harmonics. This its advantage is simple and there's no additional equipment needed in many cases. The last one is active power factor correction device, which is APFC. APFC device uh, make use of power electronics that dynamically monitor the reactive power in the circuit and maintain a high power factor. Its advantage is automatically adapts to load changes and effective for systems with rapidly varying loads. That's all from me. Thank you.
Hello everyone, my name is Teng Bao. In this video, I will show how we improve the power factor or enhance the power factor of a circuit. From this assignment, we use MATLAB software to develop the simulation circuit in order to apply the concept power factor correction. From this circuit, we had the RL series branch by setting 0.1 ohm of resistance and 1 millihenry of inductance. whereas we set 120 of nominal voltage, 60 Hz of frequency, 3000 watts of active power, and 2250 watts of inductive reactive power in RL series loads. So next, the measurement devices included are voltmeter, ammeter, voltmeter, displays, and RMS plots to calculate the voltage and current in RMS value, which produced by the AC supply. Not only that, we have used the three mathematical blocks, which are product, divide, and subtract blocks, to calculate the power factor and power loss in the circuit. So as to achieve 120 RMS voltage of source, we had to multiply 120 with root 2 for the peak value in AC supply. After designing simulation circuit, we start running and simulate the circuit. It shows power of source and power of source ability are 2657 volts and 2238 volt ampere reactive, whereas the power of load and the reactive power are 2575 volt and 1923 volt ampere reactive. Besides that, the RMS voltage of source is around 200 volt, but the value of voltage across load only have 110.9 volt is far from the value of RMS voltage of source. In the addition, the power loss from the circuit is 82.47 volt and the power factor is 0.8 and draws in 28.91 ampere of current through the circuit. Therefore, we require to add in a capacitor which parallel to the RL circuit to improve the power factor and reduce the unnecessary current. Obviously, it seems that the power factor increases and the current decreases by adding capacitor parallel with it. This causes the reducing in power loss and the voltage across load has been increased. This is because the capacitor provides a reactive power that conserves some of the inductive reactive power from the inductor and thus decrease the apparent power, which result increasing in power factor. According to the table shows below that when the QC increases, the current will be decreased and the voltage across the load will increase until it reaches the full compensation. After the full compensation, the capacitor is more than the inductive component. Then the entire load characteristic is resistive capacitive. The current power loss and the voltage across load decreases, but the power factor decreases. So it's better to keep it to full compensation level. Finally, we learned that the relationship between current and power factor and the relationship of power loss to the power factor in this assignment. To conclude, adding a capacitor in parallel with an RL circuit will increase the power factor by the concept of power factor correction. These are the evidence that we have applied the QC in negative 500 with voltage reactive, and these are the results that shows. And this is the capacitor when it parallel to the RL series circuits. It is in negative 1500 voltage reactive power. And this is when the capacitor parallel with the RL series circuits in negative 2250 voltage reactive power, and it shows the results in the full compensation level. And finally, this is the capacitor parallel with those RL series circuits in negative 3000 voltage reactive power.